triple integrals using spherical coordinates. I'm basically just going to set up the questions to the point where I think they are relatively doable, kind of the part where Calc 2 would take over. So in a version of question 7, you're doing a triple integral. The guy that we're doing is x squared plus y squared. And the region E is actually a hollow sphere. You've got a sphere with the equation x squared plus y squared equals 9. That's the inside sphere. And you have x squared plus y squared, z squared is 16. And there are no more restrictions, so that's pretty much it. So since there's a lot going on here, I think the easiest way for me to tackle it would be to find out what the limits of integration are based on the inside-outside sphere situation. And then convert this into rho, phi, and theta, and then set up the integral, and that should be good. Right. Would you agree that this guy here is just another way of saying rho squared is 9? And this guy here is rho squared is 16. That'll be fine. And so the radius is 3 and the radius is 4. So since it's the piece between those two extremes, are you comfortable about rho being 3 to 4? Does that make sense? Big sphere, little sphere, we want the between, right? Bigger than 3, but less than 4. Now, it's an entire sphere. When it's an entire sphere, then, these two guys are pretty obvious. 0 to 2 pi and 0 to pi. Are you comfortable with those two? The theta goes from 0 to 2 pi as it always does here, right? If it's an entire sphere, right, an entire revolution, which it is, right? Now, can we just pretend that it wasn't just the whole sphere, but only the part that's above the XY plane, right? So if you can imagine, there's the XY plane. We're only talking about half a sphere, right? That, well, it'd be the bit in between, all right? I won't draw that's a mess, but that would stay put, wouldn't it? Because that doesn't get changed. Which one of these, and it's only one of them, would actually be the one that you choose? And by the way, the z-axis goes right through the center. Which one of these, but only one, would you change?
P.
Okay. And what would it go from where to where?
It would go from 0 to pi over 2.
Agreed. Yeah. Right. So if you can visualize it, even if you can't draw it, it certainly helps. But this is back to the original, so that's the one we're going to do, and that is fine. Now I need to figure out what x squared plus y squared. I wish it had been x squared plus y squared plus z squared, because that would have been easy. And this time I'm going to try and do this one correctly, because I did one earlier, I think, last time. Kind of got it back to front. So we got this guy plus, I'm just going to write it underneath, because it's kind of, right, that's x squared plus y squared. You can pull out a rho squared. You can also pull out a sine squared of phi, and that leaves you with cos squared theta plus sine squared theta. You agree? Pull out a common factor of rho squared, common factor of sine phi squared, and these guys. And hopefully you say, hey, that's 1. And so x squared plus y squared becomes that guy. All right, that's all the pieces that we need. So since they're all numbers, I don't need to worry too much about the order. So I'm just doing it rho equals 3 to 4. Theta equals 0 to 2 pi. Phi equals 0 to pi. X squared plus y squared is just rho squared sine squared phi. My dv is going to get me another rho squared sine of phi, and then I can just do d phi, in this case, d theta, d rho. Would you agree that this is, as most of these questions seem to be, variable separable? Would you agree? Everybody's numbers, and these are just big multiplication. So if I take this guy and join it to this guy, I'm going to get rho to the 4 from what, 3, 4. There's no mention of thetas, so we'll just do 0 to 2 pi of 1. And then we have a sine cubed phi from 0 to pi d phi. Easy, easy. How am I going to integrate sine cubed? You know you're going to get trig in these questions, right? Spherical coordinates, you can't really avoid them most of the time. So how am I going to integrate sine cubed? What method?
Could we use a reduction formula?
Oh, interesting thought. Yes, if you could find one.
Notes I have left over from Calc 2.
Okay. This is, I think, a slightly more mathematical and less formula based. Sine cubed can be written as sine squared. Keep that alone. Can you think of a different way to write sine squared that might help with the u sub?
1 minus cosine squared.
Now, it's a u sub, but the u sub is not 1 minus cos squared, and the u sub is not cos squared. What is the u sub going to be to make this work?
Sine?
Sine.
Just cos square.
Just a cosine. Because that becomes 1 minus u squared, and won't the derivative of this kill off that guy? There'll be a minus involved, but it's still going to work. And that's as far as I want to go in that question. Next one is a triple integral, some 3D region E. It's going to be an x e to the power of x squared plus y squared plus z squared dv. And region E is not as simple as it looks. It's the unit ball, which I would call a sphere, right? So it's a unit ball, x squared plus y squared plus z squared less than or equal to 1, right? That's what a unit ball is. That's not a big deal. What's the big deal is, it's in the first octant. This is a sphere, radius 1. That's the only easy bit. Now, when they're talking about the first octant, I'm not even sure I can draw this. Can you think of one of those chocolate orangey things and you've got a big wedge that looks like that? Okay. Can you imagine taking a whole sphere, right, and only using that piece, right? That means that we have to figure out what are the restrictions on theta and what are the restrictions on phi that generate only this piece, right? Not the you know, Pac-Man side, but the little wedgie guy. Okay, now Let's do the theta. Theta is basically from here to here, isn't it? Now, if you cannot orientate it, can you see that you're going from 0 to here, right? So what would be the range in theta for the first octant now? You're starting at theta is 0, right? What would be the finish value?
pi/2.
Agreed. That makes sense from 0 to 9, 0 to pi upon 2. And you know, the rest would be here. Now, starting vertical and curving down, this is phi, right? Starting vertical, which is 0. And curving down until you hit the XY plane. What is going to be the restriction on phi then to make that happen? Right, so start vertical, and then you curve down that way.
Is it going
Also
to be
pi over 2?
Also pi over 2. Right, so you start vertical, and you get to here, that's pi upon 2. Pi would be going all the way down to the bottom again, right? So we're talking about the vertical rotation. Well, there we go. Took a bit of fighting, but there's E. Now we have x e to the x squared plus y squared plus z squared part. Okay, well, I know who you are. You are rho squared. And I know who x is. He's rho sine phi cosine theta. And while we're at it, why don't we stick in the dv? And the dv says another rho squared sine phi, and then we can do the d rho d phi, I guess, d rho d theta d phi. Right, I think we got everybody then. We're going to do phi on the outside this time. And phi goes from 0 to pi upon 2. Then we're going to do theta next, which is also 0 to pi upon 2. Then we're going to do rho, which was from 0 to 1. And then it's this horrible mess tidied up. So that's going to be rho cubed sine squared phi cosine of theta e to the rho squared, okay, times d rho d theta d phi. Well, at least it separates. So we'll do the phi's, and the phi's end up just being sine squared. And theta, well, pure theta doesn't seem to get used much, so it's just 1. And then we have from 0 to 1 of rho cubed e to the rho squared d rho.
Don't we have cosine theta?
Did I? Oh, thank you. Yeah. I'm having an issue with this guy. That one there, well, let's take it one at a time. How are you going to do sine squared? We did a couple yesterday where you had a sine squared or a cos squared in it. What do you change that into to allow you to integrate it?
One half times 1 minus cosine of 2 phi.
Okay. I won't even talk about that one, right? That's pretty straightforward. Now, the one that's got me thinking, I now have the answer, but I was clutching at straws here. We have to figure out how to do that. And I'm looking at the way they're doing it, and it's not the way I'm going to do it, so that's interesting in itself.
Isn't it U sub?
Well done. Who's your U sub going to be?
Never mind.
No,
That was
it's
U
right.
sub.
This is the way I'm doing it. It's not the way they're doing it, but it's the way I'm going to do it. So I like U sub.
Is it
Okay.
rho squared?
It is. Now you are going to, and it looks like you might have talked yourself out of doing the right thing, David, but there's a rho cube there. If that was rho, it'd be great, wouldn't it? U sub would work perfectly. It can still be done. You just have to fight your way a little bit further. So I'm going to do more with this one that I typically would do. So there's the differentiation. There's the crossover. And then you divide everybody by 2 rho. And that isolates the d rho. So it's going to be the integral of rho cubed e to the u 1 over 2 rho du. Now, one of the rows cancel, and you're looking at that. And normally that is a bad sign that maybe you've chosen the wrong U sub, or maybe you've chosen the wrong method. But it's not in this case. I have to figure out what rho squared is in terms of U. Doesn't this all have to be U's? Well, it's actually not that difficult. What is rho squared?
U.
So what you have here is a half U e to the U du. You still with me? Now, I have a different problem, and I'm now going to tackle this a different way. How are you going to integrate a half U e to the U? What method will you use this time?
Integration by parts.
Integration by parts. So make that F, make that G, and have fun. So that is a pretty messy question, isn't it? That the U sub didn't get you out of trouble, but didn't the U sub followed by an integration by parts would get you out of trouble? And obviously you keep the best till last. Any questions about that before we move on to our next section? I want to get a head start on the next section. Are we good? Okay. Close this fella off, and we are now on change a variable. We're going to do change a variable with double integrals. It is possible to do it with triple integrals. Actually, it's possible to do it with quadruple integrals and as many integrals as you like. What's the problem? It's horrendously difficult to do, right? And so double integrals are bad enough. And yeah, do you know change of variables is just the more official title for U subs. So we are going to have a different approach to U subs. We know how to do U subs with a single integral, which is fine. They work. That's what their job is. But when you do it with double integrals, the world changes quite a bit. And it's not anywhere near quite as simple as you'd like it to be. So essentially, you're going to take a function in terms of x and y, right? And you're going to change it into a new function. And this one is too difficult to do. And this one, which is equal to it, is much easier to do. And that's essentially what change of variables does, doesn't it? It takes the x e to the x squared, which is hard to do, and turns it into an e to the u or a half e to the u, which is easy to do. So what we're going to do is skill building before we even tackle that situation. So we are going to look for a guy called the Jacobian. I believe that's actually the last name of this guy, right? So he got it named after him, right? And the Jacobians look like this. We're actually going to do a partial derivative of two variables in terms of two variables, which is a weird thing, right? You all know how you do partial derivative dx by du, right? And you can do dy by du, and you can do dy by dv and dx by dv. But what we're going to do is do all of them at once. So this double derivative, partial derivative situation is called the Jacobian, right? And to do this guy, can you remember 2 by 2 matrices? And can you remember how to get the determinant of 2 by 2 matrices? Because that's what the Jacobian is going to be. So we have the partial derivative of x with respect to u, the partial derivative of x with respect to v, the partial derivative of y with respect to u, and the partial derivative of y with respect to v. And then we find what's called the discriminant of the 2 by 2 matrix, which is basically major diagonal take away minor diagonal. Remember, Calc 3, major take away minor. Right. So let's do a question. Let's suppose x was equal to u squared plus v squared. And let's suppose y was v cubed plus u. And we want to find the Jacobian. Oh, little side issue. This value, whatever it is, must always be positive. Now, the only time that's ever going to be of an issue is if this, by sheer niceness, ends up being a number, right? So if it's 42, it's good. If it's negative 42, pretend it's 42. When this ends up being an expression, you can't really deal with it. You don't know if an expression is going to be positive or negative, right? Is u cubed minus 5uv positive or negative? Yeah, right. But when it's a number, you make that little exception. So here goes. The derivative of x with respect to u is just 2u. The derivative of x with respect to v is 2v. The derivative of y with respect to u is 1. And the derivative of y with respect to v is 3v squared. And major diagonal, take away minor diagonal. So the Jacobian in this case is 6u v squared, take away 2v. Are you comfortable that as long as I tell you who x and y are in terms of two variables, that you can use this to get a Jacobian? Not yet.
I failed to do that. I need to do that today.
Say again, Andy?
Most likely, yeah.
I will mute them because he is talking to someone else, not me.
I'll have to check the schedule.
Right, let's turn back. Right, I'll ask that question again. It's so far so good, right? So if I tell you these two guys, you got a formula, plug in the bits, major, take away minor, right? So let's do this fella. Do you recognize that guy? That's polar, isn't it? Do you know that we had a funny R that came from someplace and you don't know where it came from, wouldn't you like to know where it came from? It came from the Jacobian. So you're going to do the derivative of x with respect to r, the derivative of x with respect to theta, the derivative of y with respect to r, and the derivative of y with respect to theta. Right? So that's going to be our Jacobian. Right, if you differentiate this with respect to r, you get cosine theta. And if you differentiate it with respect to theta, you get negative r sine theta. And if you differentiate this with respect to r, you get sine theta. And if you differentiate this with respect to theta, you get r cosine theta. So far, so good. Now, if you do major diagonal, take away minor, let's see what you get. You multiply these together, you get r cos squared theta. And if you take away these guys, you get negative r sine squared theta. So you get r cos squared plus r sine squared. And if you pull out r as a common factor, you get that. Agreed? And oh, that's 1. So let me add something to this up here. When you do a change in variable, the dv will become the Jacobian and then you can just do du dv. So you turn everybody who's x and y's into r's and thetas or u's and v's. You multiply it by its like a correction factor, a scaling factor, the Jacobian, and now you can integrate in terms of u and v instead of in terms of x and y. Doesn't that amaze you? Now, you know that horrible guy that we had in spherical coordinates? You know that rho squared sine phi guy, right? Remember him? Where did he come from? He came from a Jacobian where you had x, y, and z. And the 3×3 Jacobian is dx by dr, dx by d rho, dx by d phi, dx by d theta. You would end up with a 3×3 matrix. Can you imagine how horrendously ugly those questions are, right? A 3×3 matrix, you know, and you'd have to do cover it up, cross, you know, like you did cross producty thing, right? All that good stuff. 3×3 matrices, not your friend, not very practical, but that's where that came from if you're interested. In fact, if you ever came across a coordinate system that was very useful, you know, like polar is quite useful, right? If you came up with another one that was really useful, you could call it the Robertson coordinate system. And what would make it useful? Well, I can imagine situations where if you're dealing with a certain family of two-dimensional shapes, maybe everything you deal with is ellipses. Couldn't you invent a coordinate system called the elliptical coordinate system? So instead of x's and y's, can't you just have two variables, right? That describe an ellipse in a way that makes the equations nice. So that's all it is. It's a u sub extended to the two-dimensional and then from there to any dimension that you like. Okay. Any questions so far? Right now we're just doing the skill building, right? Finding these things called Jacobians. We're not going to take it any further yet. So let me find if I can find one. Here's question 3. X is equal to 7p e to the q. And y is going to be 5q e to the p. And the Jacobian is always, right, that guy. over whatever the other two variables are to be called. So partial derivative with P and then with Q, partial derivative of Y with P and then with Q. Start with this guy. If you do a partial derivative with respect to P, you get that. If you do with respect to Q, you get that. If you do this fella with respect to P, you get that. And if you do it with respect to Q, you get that. Now, major diagonal gets me 35, and if you multiply these two together, you get e to the power of p plus q. Take away, if you go this way, you get 35, you get pq, and also e to the p plus q. And you want to make it look pretty, I'd pull out 35 and e to the p plus q. And you get that.
Wouldn't it just be 1 minus PQ? Crazy? Yeah. Oh.
You all caught that deliberate mistake, guys? Okay. Only for completeness sake, we're going to show you a Jacobian with 3 variables, right? A 3 by 3. Once you've seen this one, you'll probably agree that you don't really want to do a question with it. But this is, you know, it's something that's helpful to know. So in this case, X is 7 UV, Y is going to be 5 VW, and Z is going to be 7 WU. And the Jacobian of X, Y, Z with respect to U, V, W is going to be a 3 by 3 matrix. Right, and then it's the determinant of it. So you're going to do the partial derivative of X with respect to U, with respect to V, and with respect to W. You're then going to do the partial derivative of Y with respect to U, with respect to V, and with respect to W. And for the last one, you're going to do the partial derivative of Z with respect to U, V, and W. Does that make sense? That's what a 3 by 3 Jacobian would look like, right? So far, so good. Now, second kind of step is I'm going to find all those guys. So if you do this guy with respect to U, you get 7V. If you do them with respect to V, you get 7U. And if you do them with respect to W, you don't get anything. You get 0. Start with this guy. With respect to U, you get 0. With respect to V, you get 5W. And with respect to W, you get 5V. Last one. With respect to U, you get 7W. With respect to V, you get 0. With respect to W, you get 7U. Does that look good? Now, I know it's a fair amount of time, but can you remember doing those cover me up in 2 by 2 matrices, right? So that's what we're going to do. So the first guy is 7V. And then you cover them up. And when you do that, the first column, you've got major take away minor, which is that guy times that guy, which gets me 35 UW. That's the first one done. Now, You do the second guy, and it's negative, the second guy. And you cover them up, and it's 0, take away this fella. So it's negative 35 VW. And then you go to the last one. Well, the last one's easy because it's 0 times I don't care. Because 0 times n is just 0. If you multiply all these pieces together, you get 7 times 35, which is 245 UVW. And 2 negatives make a plus, and you get 245 UVW. And so you end up with 490 UVW. Now that's probably one of the simplest 3x3 Jacobians you could get, because aren't there a lot of zeros around, which tend to make it a little bit easier to do. Now, if you wanted to do the spherical coordinates, wouldn't you just replace x by what it was, y by what it was, and z by what it was? Do all of these guys, right, with r, with phi, and with theta. Have a really messy version of this. 2 pages later, things would cancel out and things would combine, and you get that, you know, the rho squared sine phi that you get when you do your spherical coordinate system. So now, got time? Yes, we do. Let's look at this finding a Jacobian where they do things like this. They might give you the information written like that. In fact, most of the time, that's actually the way U subs work. Don't you tell people U equals x squared? You don't tell them x is the square root of u, right? You don't do it that way around. But in the world that we need, don't we need to have this rewritten, right? These two equations, don't we have to have them rewritten where x is a function of u and v and y is a function of u and v, because we have to do a Jacobian, right? And we need x's with u and v's, and we need y with u and v's. So now we have a problem. How do you solve a system of equations where everybody is a variable? And we want to solve it so that x is equal to some combination of u and v, and so is y. I've set this one up as one of the simplest versions of that question. Can somebody tell me what would be the next line of algebra? Think of solving by the addition method, because
Do we
that's
add them?
you do. And so you get u plus v is equal to 2x. Do you see the y's get cancelled there? Which means that if you divide everybody by 2, haven't we now got x in terms of u and v? Agreed? So far, so good. How do I find out what y is equal to in terms of u and v?
Subtract.
What a cool idea. Yes, but in general, that would work fine. But in general, because most of the time this is going to be 2 and this is going to be 5, right? So it's going to probably not work quite as well. But yeah, that would work. But tell me another way.
Substitute.
Yeah. So I'll take equation 1 because I want to. And I'll replace the x by that. And if I subtract a half u from both sides, and if I subtract a half v from both sides, I now have that guy. So the original information wasn't given in the form that I need, but you see how I've managed to transfer it into this format. Now, if you want to do the Jacobian, which you do, it's going to be the derivative with respect to u, the derivative with respect to v, then y with respect to u, and then y with respect to v. And there's going to be a lot of halves around here, so be careful. A half, a half, a half, and a negative a half. Now, when you multiply this guy, you get negative a quarter. Take away another negative a quarter. The answer is negative a half. Now, what did I say about a Jacobian that is important in this question? The answer is not negative a half.
You want to take the absolute value of it.
Right. Now, when it's an expression, that's not really an issue, right? But when it's a number, it might be. Now, here is a little trick of the trade that is usable in some circumstances. I can actually find that guy relatively easy, right? Because isn't the information written the way I want it to be? And I'm going to find that guy. So differentiate this with respect to x, then differentiate it with respect to y, then take v with respect to x and take v with respect to y. And a whole load of numbers going to have 1, 1, 1, negative 1. Negative 1, take away 1, negative 2, we call that 2. Do you notice anything connecting those two Jacobians? What time for my pen to run it?
They're the inverse of each other.
Reciprocals. Yeah. Now you might think, well, that's a coincidence. So here is a little sneaky thing.
I'm sorry, could you go back? I'm having a hard time figuring out how you got a positive 1/2 u.
Oh, okay.
minus-
If you multiply these two together,
No,
you
no,
get one.
up to more. Sorry.
Are we good? Christian, what's your question? Are you good?
So,
Right here, well, let me do it. 1/2 times negative 1/2. Take away 1/2 times a half. Negative a quarter, take away a quarter. That's where the negative a half came from.
how's that u on for y positive though? You see how you got 1/2 u minus 1/2 v equals y?
Oh, okay, let's see. Is it one of these guys
No,
here?
you gotta go up the next circle up.
Here?
I guess I'll just ask later, I guess. Right there.
Here, where my finger is.
Yeah. How's that
Right.
positive?
1 u, take away a half u, leaves you with positive a half u.
Oh, I just moved it over. Okay, never mind.
We're good. Right.
Got it.
So here is a little bit of a cheat. That guy is the reciprocal of that guy. Now, that reciprocal rule is only to be used when both equations are linear. What I mean by that, as long as this is 4x plus 10y minus 50x plus 60y, right? As long as it's linear combinations of x's and y's, you don't need to do all of this, whatever, all of this here to get the answer. Can't you just leave them as they are and then just take the reciprocal? Now that is only, repeat that again, it's only going to work when the things are linear. Now, if the things are not linear, like u is x cubed plus y and v is x squared minus 2y, right? Things like jumbled up, right? This technique won't help you any because your answer won't contain U's and V's. Your answer will contain X's and Y's, which means you still have to do the algebra to figure out what to turn them into, right? So you don't get any benefit. But as long as they're linear, won't these always be numbers? And as long as it's a number, your answer is fine. You can just do it and turn it upside down. Are we good? It's not going to save you, to be honest, a chunk of time, but you know, a couple of Jacobians that you want to do quickly, that would work. But last name and
So the first one was going back to the first, the spherical coordinates.
yes.
When you said, what is Z equal to? It's rho cosine.
Oh God, I will show you because I'll screw it up if I try and rely on my memory. Wow, that's a lot of paper.
Because I'm pretty sure it's phi, but the notes said theta. But then the homework was docking me points because I kept saying theta.
Well,
And it said that it
it's
was
what I
phi.
wrote down, and I hope I didn't screw that up because it's easy down because I don't memorize the spherical ones, are just too messy to do that. Here is the guy I'm looking at. And then if that works, then that's fine. If it doesn't, I'm going to have to, right. Is that what you got?
So yeah, it said that the X and the Y values were great. But whenever I replaced
this is
the
a phi?
Z value, yeah.
Oh, okay.
Or
could be me.
that's what I assumed.
Yeah.
So
Okay, that makes sense.
okay.
Okay.
And then the other thing was, can you show me how to do a 3x3 matrix? Because that was really confusing to me.
Okay, so I'll just put in any old thing. Suppose you had X, Y, and 2W, right? And 3, 0, 5, and 6, Y, and 1, right? Just for argument's sake. Right. You take that number first, X. You then remove the row and column that X is in. And the 2x2 matrix that's left, you do major diagonal, take away minor diagonal. So that would be 0, take away 5y. So that's negative 5y, and that's your first term. Then, rather annoyingly, the middle one is a negative. You use that guy, and then you cover up the row and the column. And the 2x2 matrix that you've got is major 3, take away minor 30. So that's what? Negative 27. And then you're back to plus again for this one. And you do major diagonal 3y, take away minor 0. So you get 3y. And in this case, then you get negative 5xy plus 27y plus 6wy. And if you want to make it pretty, you could probably pull out a y as a common factor. And that would be the 3b3 matrix. So that guy times the 2x2 that's left, minus the middle one, times the 2x2 that's left, and plus the last one, times the 2x2 that's left.
Okay, that makes sense.